Sir Anthony Leggett, we are so happy to have you visiting us here at Perimeter Institute today, and we're so thrilled that we get to chat with you for Conversations at the Perimeter. Thank you so much for joining us.
A pleasure. Yeah.
So I know that you've visited Waterloo many times, but it's been a few years, so can you just tell us what it's like to be back?
Oh, it's a very pleasant feeling. I really enjoyed my time working here in Waterloo, and I'm just sorry that I couldn't visit more often over the last 5 years for various reasons. But it's interesting to see how the town, particularly in this area, has changed. I'm just very, very glad to be back.
What are the biggest changes that you've noticed?
I think probably the railway. When I was last here, the railway was under construction. It wasn't running, but it nevertheless made a huge nuisance to getting around town, and that now seems to have been completed, and so everything seems much more normal and pleasant in this particular area.
I remember for years, many years in a row, you came to the Institute for Quantum Computing to teach a summer talk, and I would see you. I worked there for a number of years myself, and I would see you arrive on your bicycle and go home on your bicycle, and I remember the chaos that the construction caused. So I'm glad the construction is behind us.
Yes,
can you tell us what it was you were doing at the Institute for Quantum Computing?
That's actually a good question, and I think the most accurate statement is that I was trying to learn about the current developments in quantum information, because while I have a certain history in the area of quantum foundations, I missed out on the early developments in the quantum information revolution, and was only too anxious to pick them up from what was obviously the world's leading place in this area.
That's funny that you came to learn, and every summer students would come to learn from you. You hosted a series of talks, and I remember they were highly popular and sought after. Yeah. So I guess it was a two-way street.
Yes, well, I think I tried to put across some of the things I'd picked up in condensed matter physics, which was not something, at that time at least, in which the IQC was primarily specialised. And on the other hand, I was trying to gain the latest developments in quantum information.
You know, in preparing for today, I was trying to think, what kind of questions can I ask you that really kind of encompass a lot of the different types of work that you've done and that you have done. And one thing I thought about is that a lot of your work really relies on systems being at very low temperatures.
Yes,
so could you tell us what is so special about low temperatures?
Yes. Well, basically, I think it was put rather well by Kamerlingh Onnes, who's in some sense the father of low temperature physics as we know it today. When he got the Nobel Prize, and I think it's probably 1914, thereabouts, but anyway, sometime around then, he said, among other things, that by going to low temperatures, we draw away the veil, I think he called it, that at ordinary temperatures, noise draws over the phenomena predicted. I don't think he actually said predicted by quantum mechanics, because the whole idea of quantum mechanics was only just being born at that time, but by microscopic physics or something of that kind. So basically, by going to low temperatures, you get rid of a lot of the noise, which is irrelevant to the real phenomena you're trying to study. In this case, particularly quantum mechanical phenomena.
When you say noise, I think a lot of us think of a sound, a very loud sound, but that's not what we're talking about necessarily.
It's a more general concept.
Can you explain what noise is and why low temperatures eliminate it?
Yeah. Noise is, well, basically anything you're not interested in. And
sounds right.
generally speaking, that if you're studying a particular system, say a set of atoms, what you're not interested in is going to be random effects coming from the environment. And crudely speaking, the magnitude of these random effects is proportional to the temperature.
Okay.
So if you go to low enough temperatures, you get rid of most of it. And people nowadays have gotten extremely good at devising means, first of all, getting to low temperatures, but when you're at low temperatures, shielding out anything that's left, as it were.
Mm-hmm.
And you've already sort of alluded to this, but I think in the past and maybe still sometimes today, people tend to associate quantum physics with effects at the microscopic level, but a lot of your work has shown that we can see quantum effects at the macroscopic level and with our own eyes. Can you tell us about some of those effects that you've studied and what makes them quantum?
Sure. I think one really has to distinguish between two different meanings of the words quantum mechanical effects at the macroscopic level. One kind of effect, which we've actually known about for a long time, is when you have a large number of microscopic entities, let us say atoms, or helium atoms, for example, and for one reason or another, they're all constrained, at sufficiently low temperatures, they're all constrained to be behaving in exactly the same way at the same time. See what this means by an analogy. Suppose that I'm on a mountaintop and looking down at the main square of a city below the mountain. And first of all, suppose it's a market day when all the citizens are just going about their business, and their business, of course, is different in each case. And so looking down from this great height, it's very difficult for me to see what any particular one of them is doing. But now suppose it's not the market day, but it's the day of a military parade. Now, then you have a whole squad of soldiers marching exactly in lockstep, all doing exactly the same thing at the same time. Much easier to determine what it is that they're commonly doing. Mm-hmm. And it's pretty much like that with the atoms or electrons or pairs of electrons. The most spectacular effects of this nature are probably those associated with superfluidity or superconductivity. In the case of superconductivity, for example, it means something like the following. Suppose that I take a... This is actually a demonstration which I do quite frequently at the farmers' market in Urbana for school children and so forth. So what you do is you take a simple copper tube, maybe this kind of radius, and first of all, just to show the kids that there's nothing at all suspicious or weird about the tube, we just take a pebble and drop it down, and it just goes down, right? Mm-hmm. Next, you take a little magnet and you try to drop it down, and of course it does not drop instantaneously. It takes a few seconds to do it. And you explain to the kids that this is because the magnet, as it falls, it's inducing an electric current circulating around the tube. This, in turn, is producing a magnetic field which tends to sustain the magnet. So it does fall down, but the currents, of course, although they're generated by the falling magnet, they tend to die away. And as they die away, the magnet can fall a little further, and so on and so forth. And then you ask the kids what they expect to happen if, for some reason, the currents never did die away but just kept on circulating. And some of them may come up with the answer, well, then the magnet is never going to come out of the bottom of the tube. It's just going to hang there forever. And then you show them that if I take a pellet of yttrium barium copper oxide, one of the so-called high-temperature superconductors, I dunk it in liquid nitrogen, and then I take a little magnet and try to lower it onto the pellet, then it will not fall. It will just stay there suspended until eventually, of course, if I don't keep pouring nitrogen, the nitrogen will boil away. The YBCO, the compound, will just revert to its normal state, and then indeed the magnet will fall down. But then I tell them one further subtlety. Okay, let's imagine I don't do the experiment that way round, as it were. What I'm going to do this time is to first take the little metal pellet in the normal phase, at room temperature. I'll place the magnet on top of it, and now I'm going to pour liquid nitrogen on it so that it will cool down into the superconducting phase. Then what do you expect to happen? And it's pretty difficult, actually. I don't think people usually guess this right. If I do the experiment right, and it does take a little manipulation, but if I do it correctly, then what will happen is that as the pellet goes superconducting, the magnet will actually lift off spontaneously and just sort of hang there in midair, which is unfortunately, it's not too easy to do that experiment with large magnets. They're usually pretty tiny, so you have to squint fairly hard to see what's going on. But nevertheless, it's quite spectacular to see this thing lifting off spontaneously.
How do children tend to react to seeing this experiment?
They're fascinated, usually.
You must get all kinds of reactions.
Yes. But
And this is something you say you do fairly often to
before the pandemic, yes, I used to volunteer for the physics department's slot at the farmers market a couple of times every fall semester. Really.
Mm-hmm. And why is it that you like to do those demonstrations for young people? As a professor, you're probably typically speaking to university age people.
Yeah, but it gets them fascinated with physics, and I think that's it's always worthwhile.
Yes.
Do you think that those kind of demonstrations are able to convey an understanding of superconductivity even to young children?
Well, probably not, to be honest. In fact, I say probably not because I've actually, for the last few years, I've been teaching a course at Shanghai Jiaotong University in China, where I have a visiting appointment. And this course is to third or fourth year undergraduates, physics majors. And I've done everything that I can possibly think of to really convey an understanding of superconductivity in what I think is relatively simple language. It never works. They always complain it's much too hard and advanced for them. And these are not are not dumb students. I mean, they're pretty smart, but nevertheless, it does seem rather hard to get across the true essentials. I think it's rather easy to give, as it were, a slick and a rather misleading picture of superconductivity, but to actually convey what I think is the essence is pretty tricky.
Mm-hmm. So. Speaking of explaining superconductivity to children, we were going to wait until a little later to ask children's questions, but there's one specifically that we received from a young student named Damir, and I'm wondering if we could play that because it's very much on this subject.
Hi, my name is Damir, and I'm in grade 8. Why is superconductivity important in our lives today other than MRI machines? Do you think they have a hidden use?
Already, superconductors are being used for, I don't know what the right word is, but in the United States, there are three major power grids. And it's very important to be able to switch power from one grid, which may be overloaded, to another one which has sufficient current carrying ability. And apparently, I'm told there is a particular place somewhere down in Texas which brings the three grids together and therefore is able to switch power between them. Mm-hmm. Now, if you do this with just using ordinary metals, which are not superconducting, then one problem is that the device, I think the device itself, may overload and cause catastrophic failure in the grid. However, if you have a superconductor, you can. It has the interesting property. If you try to drive too high a current through it, it will just revert to its normal phase and therefore no longer be superconducting. Mm-hmm. So it's an automatic limiting feature. And as I say, this right now is being used in the technical device in Texas, but in future, I think there's every prospect it may be used for long-distance current carrying. And that'll have the additional and very important benefit that know that as long as the metal stays superconducting, no power is going to be dissipated in the transmission itself. Today, something like 10% of all the power, electrical power, which is produced, let us say, in a coal-fired power station or a nuclear power station or whatever, 10% of it gets lost on transmission to the place of use, which might be ordinary domestic housing. Mm-hmm. If we can, in fact, find superconductors which are remain superconducting at reasonable, say at room temperature, and are importantly, are sufficiently cheap to make, then they will dissipate no power. We'll have saved 10% of all the power produced, and that's not by any means a trivial thing.
Yeah, especially at times when there are energy crises and growing populations. Can you tell us what is the hurdle to attaining that? Why don't we have that already? Why is it so difficult?
For many years, it let us say, certainly until 1986, there was a general belief that superconductivity could only occur at temperatures below about, say, a tenth of room temperature. Mm-hmm. The reason for that is somewhat complicated, but typically one factor which comes into the expression for the maximum temperature of superconductivity is the characteristic temperature associated, so-called Debye temperature, associated with the lattice vibrations in a metal. Mm-hmm. And typically that will itself be something of the order of room temperature. And then you find that there's another factor which annoyingly never seems to be quite equal to 1. It can be, say, a tenth or 20th, but it's never really quite equal to 1. So when you take those two together, multiply them together, you get something like about a tenth of room temperature. And as I say, this is the general belief in the community for many, many years. However, in 1986, the high temperature cuprate superconductors were discovered. They are a rather special class of metals where it turns out that first of all, the mechanism of superconductivity appears to be quite different from what it is in the more traditional superconductors. And so these factors really become irrelevant, and what governs the transition temperature, the highest temperature at which you get superconductivity, is something different. Mm-hmm. And so initially, these were discovered to be superconducting at something like 90 or 100 degrees absolute, so about a third of room temperature, and that was already a big leap forward. But people were very optimistic in the early days. They thought, okay, well, if we make it a third of room temperature, then why not room temperature itself? Unfortunately, it turned out to be not quite that simple. They got up to about half of room temperature and then it stuck. And it's been stuck there for, 30 years now, I think, probably. In the meantime, something else exciting has happened. People indeed do now have essentially superconductivity at room temperature, where they've actually got up to 273 degrees absolute, or it is 300 degrees absolute. I'm not sure, it's probably 295 or something, but anyway, it's essentially room temperature. However, there's a rather major snag. You can only do this under really, really huge pressures. The kind of thing you can only get in a diamond anvil press, for example. Not the sort of thing you can just turn a knob and get it at room pressure. So people have all sorts of ideas about how you might get around this problem. For example, you might try to produce the superconductivity under these very high pressures and then gradually relax the pressure and so forth, and some of those might work, but so far we don't actually have robust superconductivity under ambient conditions, meaning at normal temperatures and pressures, like in this room now. So I think we'll get them, but I'm an optimist in that respect.
That was my next question. Are you an optimist that we'll get there? But you just said so.
I think I am. In fact, when I talk to an audience of school kids, I often predict that if not in my lifetime, at least in theirs, we will have room temperature superconductivity, and then we'll have all these marvelous science fiction-like scenarios of people sort of being conveyed from one place to another on these floating superconducting magnets and so on and so forth.
And earlier when we were asking you about these macroscopic quantum effects in general, you made this nice analogy to this military parade. Yes. How do I think of that military parade in the context of superconductivity?
Okay. There are really two, I would say, but other people might disagree, but I would say that there are two major phenomena which in some sense, for me at least, define what I mean by superconductivity. One of them is the sort of floating magnet effect, which is very spectacular, very characteristic of superconductors. The other is, in some sense, less spectacular. It's simply that if I take a ring, say, suppose I take an ordinary copper ring, and I generate what we call an EMF, a voltage around the ring, or electric field, if you like, around the ring. I can do that, for example, by waving a little magnet in the vicinity. Then that will generate an electric current. But if I'm talking about just something like copper, an ordinary metal, once I've stopped waving the magnet, the current will just die away. And it'll die away on a very short time scale, maybe a billionth of a second or something like that, very, very fast. If, on the other hand, I take a superconducting ring, do the same thing, I wave the magnet around, generate a current, start circulating. But now I take the magnet away, nothing happens. The current continues to circulate. Okay, so now in terms of the platoon of soldiers analogy, think first about the normal metal. And so, rather than a marketplace now, think about a forest, a natural forest, not a plantation. So the trees are just arranged at random. And imagine I take a group of school kids and I simply tell them to run into the forest, and I start them all running off in a particular direction. But I don't give them any further instructions than that. Well, fine. They'll start running all in the same direction, but eventually one kid is going to run up against a tree. And so having no special instructions, she will swerve to avoid it and end up running in a different direction. And after a few minutes, you can see that all the kids are going to be running around in completely random directions. So that's the analogue of what happens in a normal metal like copper. You start the electrons off all going in the same direction. Then they bump into, in this case, impurities in the metal, be scattered in random directions. As it were, no special instructions. So they stay in the new direction, and after a short time they're all running around at random, so no total current. The currents just cancel. But now, okay, let's think about the superconductor, and let's think about in this case, actually it's not single electrons, it's pairs of electrons, which makes it a little more complicated. So I have these pairs of electrons, which I send off. Again, I send them off all running in the same direction. Well, again, one of the electrons in the pair, or maybe the two, run up against an impurity. So they swerve to avoid it. But the crucial difference is that they now have instructions. They've all got to keep in step at least as far as is possible. So having swerved to avoid the impurity, they will drop back and get in step with all the rest. So they'll be like the platoon of soldiers rather than the kids. And so the current will continue essentially to flow for as long as I want to look at it.
And that's due to the makeup of the metal itself, its internal structure?
That's a very complicated question, actually. In other words, what exactly is it that makes some metals superconducting and others not? In the old days, it used to be thought the answer was at least somewhat straightforward. You've got to be able to form these pairs of electrons. So in order to do that, you need some kind of effective attraction between them. The problem is that if you just think about the direct Coulomb interaction between electrons, it actually is repulsive. So it's not going to help you to form pairs, or at least not obviously. However, it turns out the subtlety, and this was the work of my former colleague John Bardeen and colleagues, plural, John Bardeen and David Pines at the University of Illinois, way back in the 50s. They realised that that what could happen is something like this. One of the electrons is coming through the lattice, and it's coming in some sense quite fast. As it comes through, it will tend to attract the ions of the metal, which are positively charged. So the ions will tend to congregate towards the path of the electron. But the electron is rather fast and the ions are rather slow. So long after the electron has gone away again, the ions will still be left there, sort of hanging around around the path where the electron was. That, of course, forms a positive charge, and a second electron is now attracted to that. And so the second electron is attracted not to where the first one now is, but where it was in the recent past. And it turns out that is a very effective way of forming these pairs, so-called Cooper pairs of electrons. And that is thought to be the mechanism of superconductivity in the old-fashioned superconductors. The metals which don't become superconducting are simply those which this effect is not strong enough to outweigh the original Coulomb repulsion. And that's a very detailed matter, which is difficult to get right from first principles, though people are getting better at it these days. But now in the more recent superconductors, like the so-called high temperature ones, the cuprate superconductors, almost certainly that's not what's happening. Something different is happening, and although one doesn't know in detail what's going on, what seems to be likely is that already in the normal phase at, say, room temperature or whatever, these metals are what are called strongly correlated systems, which means that the Coulomb interaction already has had a large effect and governs the relative behaviour of the electrons and so forth. And so what you're doing, what happens when the Cooper pairs form, in this case, is not that you've produced, as it were, a new attraction between the electrons, rather you've reduced the original repulsion. And that makes it advantageous to do it, as it were. As I say, I think most people would agree that that's the sort of very general scenario, but to actually dot the I's and cross the T's is by no means trivial.
Much more complicated.
So there really is no universally agreed theory of the cuprate superconductors in the sense that there was of the old-fashioned ones. What I talked about was explicitly superconductivity. Superfluidity is a very similar phenomenon, but occurring in a electrically neutral system like, say, liquid helium. So it's basically the same conjunction of effects, but in slightly different disguise because you're talking about a neutral system. Mm-hmm. So, for example, in the case of the persistent currents, it's basically the same as in superconductors. If I take a ring, sort of annular flower ball kind of geometry, put liquid helium in it, and I somehow managed to get it circulating. If it's in the normal phase, again, it'll just stop after a minute or two. If it's in the superfluid phase, it'll basically continue to circulate forever, just as the electrons did in the superconductor. Mm-hmm. So that's a straightforward analogy. But in the case of the levitated magnet is a little more complicated. In this case, what happens is that if I, again, take an annular ring, put it, say, on a old-fashioned gramophone turntable and start the turntable rotating. Again, if it's in the normal phase, it'll, just like water, it'll eventually come into rotation with the... So I may put this glass on a gramophone turntable and rotate the turntable. It'll take a few minutes, but it will eventually be rotating with the turntable. If I do this with helium at sufficiently low temperatures, it will it will refuse to rotate with the container, and it'll stay. Well, at first sight, at least, it'll stay stationary in the laboratory frame of reference. Now, if you think about it, you might think, well, wait a minute, that's a bit suspicious because, after all, the laboratory is itself rotating with the rotation of the Earth, mm-hmm. etc. Is it really stationary in the laboratory, or is it really stationary in the frame of the fixed stars? Mm-hmm. And the theoretical prediction, rather confidently, is it's stationary in the frame of the fixed stars. Experimentally, it's a little less clear, but it's consistent. I should say the experiments are consistent, at least mm-hmm. with that being the right answer. Anyway, so superfluids then are rather closely analogous to superconductors. On the other hand, again, a consequence of a very large number of microscopic objects, in this case the atoms, being constrained to do the same thing at the same time. The other kind of macroscopic quantum effect, which is what I've been more specifically interested in over the last 30, 40 odd years, is that in microscopic physics, you very often get the situation that a microscopic object, let's say an atom, it appears to behave in a different way depending on whether or not you're looking at it. So the standard example of this is a so-called Young-Slits interference experiment, which was originally done by Young himself with light, He didn't know in those days that there were photons. But nowadays it's done with electrons, and the late Akira Tonomura in Japan did a whole series of very convincing experiments on this. And so, at least in principle, you can do the experiment this way. You take a source of electrons. Well, you have to sort of tune the knobs on the black box rather carefully to make sure they're the right electrons, but you can do it. And you allow them to go through one of two paths and eventually arrive at a final screen. And if you just set it up that way and you don't look at what's going on, as it were, then you find you get a standard pattern of bright and dark lines on your final screen. And you can actually, the way that Tonomura does it, you can actually see, as it were, the individual electrons coming through one by one and gradually building up this pattern. So it's clear that that's what they're doing when you don't look at them. On the other hand, if you try to detect which of these two paths a given electron took, you always see it took one or path or the other. Then you destroy the interference pattern. Okay, so you have the choice between observing which path it took or observing the interference pattern. This is an example of what Niels Bohr called complementarity, basically. In the early days of quantum mechanics, it used to be thought that somehow this phenomenon, so-called interference or phenomenon or quantum superposition, this was limited to the microscopic world, atoms, electrons, and so forth. Then Schrödinger, through, well, let's say, if I make a pun, a cat among the pigeons, by his famous cat thought experiment, he envisaged a situation in which if the electron in question, I actually had a slightly different setup, but let's say the electron in question, if it went one way, then it would trigger some kind of counter or whatever, and as a result various things would happen at the everyday level. In his case, he had a cat inside a closed box, and the cat would die. It would actually not be, as many people erroneously think, it would not be shot or electrocuted, it would actually be poisoned with cyanide, but that's a detail. Anyway, the cat would end up dead. If the electron went in the opposite, along the opposite path, nothing would happen. The cat would stay alive. Okay. Now, the thing is that it's not an experimental, it's not a directly observed experimental result, but it's a very firm prediction of the formalism of quantum mechanics that if you're not looking at the experiment, as it were, the correct description of the electron at the intermediate stage is that it's neither doing one thing nor the other. It's in a so-called quantum superposition, and it's only because it's in this quantum superposition that it can later cause the interference phenomenon on the screen. On the other hand, if you look at it, then it appears to choose one alternative or the other. Well, what Schrödinger was pointing out, basically, was that that if you believe, as he and most of his contemporaries believed, that quantum mechanics is the whole story, then you observe that the formalism of quantum mechanics has a very characteristic property. However complicated the system you're talking about, if you start off with two possibilities, A and B, say, if alternative A initially leads to alternative A prime at the end of the day, alternative B leads to alternative B prime at the end of the day, then the quantum superposition of A plus B leads to the quantum superposition of A prime plus B prime. It's a very, very fundamental feature of the quantum formalism, and if you deny that, you're no longer really believing in quantum mechanics, you're believing in something else. Okay, so in his case, in the case of the cat experiment, since the electron started off in the linear quantum superposition of these two possibilities, then finally the cat, or more accurately, the universe containing the cat, must end up in a quantum superposition of these two possibilities. And yet, I don't think anyone doubts that if we were to do this experiment, and fortunately animal protection societies have prevented us doing it in a statistically significant way, but if we did, then in each individual case, when we opened the box, we would definitely find the cat to be either alive or dead. And that's basically people usually call it the quantum measurement paradox. I prefer to call it the quantum realization paradox. The fact that at the microscopic level, no alternative is definitely realized. At the macroscopic level, it fairly obviously is. When Schrödinger first put up this paradox, it isn't clear how seriously he himself took it. Really, he calls it there's a word I know I've forgotten, but it means something like a bizarre or whatever experiment. Anyway, people shrugged it off basically, and the reason that most people shrugged it off was the phenomenon was called decoherence, which means that so long as I have a system which is sufficiently isolated that I can try to describe it entirely in its own right, as it were, for example, a beam of atoms in vacuum, something like that, then I can simply write down the textbook quantum mechanical formulae. But the moment that system starts to interact with any kind of environment, that means anything I'm not interested in, really, the environment will come in and try to screw things up. And so, and in particular, what it'll try to do is to randomize the relative phase of the different components of the quantum mechanical wave function. A slight oversimplification, but it basically conveys the essence. So, since the interference pattern depends very crucially on the relative phase, this means that the moment the environment screws things up, you no longer get the interference effect and so forth. So all your predictions are just as if the electron had gone through one slit or the other, but you just don't know which. In technical language, it means that the off-diagonal elements of the density matrix go away. Anyway, so a lot of people just basically shrugged this off. And this is an argument which recurred, and even through the 70s and 80s, you were still finding people publishing papers claiming to resolve the cat paradox this way. So I started asking myself, well, wait a moment. Is that really true? Is it really true that by the time we get... incidentally, I should have added one thing. The further you go from the microscopic level, the level of the electron and the atom, to the macroscopic level, the level of the cat or the Geiger counter or whatever, the more important these interference effects generally become, the more effective they become. So that most people agree that under most circumstances, by the time you've got up to the level of cats and counters or whatever, none of these interference effects really are left at all. And people just were happy with that. Or a lot of people were happy with that.
Not you?
Not me. And actually, I should say not some rather well-known other people like John Bell. But that was a minority point of view. So sometime around the late 70s, I started asking myself, well, can't we somehow get around the decoherence objection? That is, can't we devise a situation in which quantum mechanics, if you do take it seriously, as Schrödinger had done, quantum mechanics really predicts that a macroscopic, genuinely macroscopic object is in a quantum superposition of macroscopically distinct states. And can we then now try to indicate that it's in those that superposition by getting it to display interference effects the same way as the electron did? And I basically my shorthand for this this program of research, which I was not going to do myself because I'm not an experimentalist, but I was going to try to persuade some of my experimental colleagues to do it. My shorthand for it was building Schrödinger's cat in the laboratory. Okay, so when I first I was not incidentally, I was not the only person to think of this, but I think that the one or two other people who did propose things along these lines had really not taken the decoherence objection seriously, and I thought it was really necessary to do that. Anyway, there's a huge cry of objection from the whole professional quantum measurement community. I mean, there's this whole group of people, usually sometimes in departments of physics, more often in departments of philosophy or mathematics or whatever, who basically made it their life's work to implement the decoherence argument in more detail and to show that you could never see interference at the macroscopic level. So, of course, all these people are up in arms and very indignant I suggested any such thing. And so with the whole series of exchanges over the next 20 years or so in the pages of physical review letters. Luckily, very luckily, my experimental colleagues are much more open-minded, and which is something I've found actually much more generally, in fact. And so several experimental groups did start off in the early and mid-'80s to begin implementing this program, and it had to go at a sort of measured pace. But by around 2000, they had got to the point where they could show that at least in a certain kind of superconducting device, technically called a, well, it used to be called a RF squid, but nowadays it goes by a more fancy name, the name of flux qubit, because it's used in quantum computing. Anyway, in this kind of device, you got a situation where quantum mechanics appeared to predict that you would get these interference effects, and experiments seemed consistent, at least, with it. However, that was not the end of the story, because the mere fact, obviously, the mere fact that quantum mechanics predicts a certain kind of effect, and you see this effect experimentally, doesn't prove that quantum mechanics is right. Mm-hmm. What you would rather do is to prove that some alternative class of theories is wrong. And that's that's logically a much more sounder argument. And so I and others did some analysis for this, and eventually we did get around to an experiment. This experiment was done by a group at NTT in Japan in 2016, and I'm a sort of incidental co-author on the paper, but sort of rather tangential to it. Sure enough, that experiment did seem to show not only that quantum mechanics was working, but that a whole class of other theories in which things at the macroscopic level, things do one thing or the other, was not working. And so I think that's been at least somewhat satisfying since it's got that far. Where we go from here, of course, is anyone's guess. My own feeling is that we're not at the end of the road, and that if we push things far enough, and particularly if we push them far enough in the direction of direct human perception, that we will get a surprise at some point, that something will go wrong. We don't know what, but we don't know when, but we do know it will go wrong.
You seem excited about the prospect of things going wrong, which isn't always the case.
Interesting. Yes.
You've mentioned a couple of times collaborators around the world, places like China and Japan. And when we were chatting with you the other day, you mentioned how important your travels to other countries have been. And we actually have a question that we'd like to play for you on that subject.
Okay.
I'm David Pomeransky, and I'm currently a researcher in Japan at the Institute of Physical and Chemical Research. Here it's commonly known as RIKEN. I really enjoyed taking your course on topological superconductors in Waterloo back in 2016. Thank you very much for taking my question. I've noticed that you've lived in several distinct places throughout your career. I think this is one of the great opportunities of being a researcher. Can you comment on the factors that drove you? What were the pros and cons of these experiences in shaping your career?
Yeah, thank you. That's a very interesting question. I think my original motivation for spending a postdoctoral year in Japan, which is my first major foreign excursion, was simply curiosity. I'd always been curious, but to try to learn about the culture, history, and to some extent languages of Northeast Asia, both Japan and China. At the point where I had the opportunity of possibly taking a year abroad. I should say, incidentally, this was by the kindness of my Oxford College, who interpreted the terms of my fellowship very liberally to allow me to spend a year of the fellowship in Japan. At that particular point, there was no realistic opportunity of going to China. It was in the last days of the Cultural Revolution, but Japan seemed also very attractive, and so I was able to get a position at least a desk in the group of Professor Takeo Matsubara in Kyoto, and so the prospect of living in a new society and culture, learning a new language, and trying to operate in it were a challenge, which I rather looked forward to, and indeed I think that's how it worked out. I made many friends in Japan, and many of them I've kept in touch with throughout my career. I think by living in a culture where the things which are obviously taken for granted in one's own culture, for example, in the degree to which certain kinds of human relationship impose privileges, or on the other hand, responsibilities. These are really quite different between, say, Europe and North America on the one hand, and Japan on the other, and so I find it very mentally stimulating to experience this and to think about and try to operate according to a set of slightly different rules and so forth. Again, learning a new language. I assume that since you, the questioner, that you are in, you say you're working at Weekend now, and I assume you're also learning Japanese and so forth. Maybe perhaps share this experience. I find learning a new language, not just a new language, but a language with a very different structure from most Indo-European languages. It's almost like learning to use a new muscle which you didn't know you had. So again, very stimulating, very exciting, I think.
You're making me nostalgic because in my early 20s, I spent 2 years in Japan.
Oh,
so
really?
all of these experiences of learning a new language and learning a new culture.
I didn't know that. So.
Yeah,
Okay,
yeah.
yes.
It was a wonderful place. What years were you in Japan?
The first year was 1965 to 6. The second year was after I got married. My wife is Japanese, and we spent the year 1973, or most of the year 1973 to 4 there. Yeah.
And you've told us about other travels as well.
Yes.
I remember you mentioned some work that you did in Ghana, in
Yes,
Africa.
that's right,
Could
yes.
you tell us what motivated that and what you
yes.
got out of it?
Yes, that was, well, I mean, it's possible I would have gone anyway, but had I found a different means of doing so. But really, in that case, there were no obviously set up arrangements. I mean, there were no major university groups, say, and my subject working in Ghana. And so the way that worked out was that when I and the person, Douglas Brewer, who eventually became Professor of Experimental Physics at Sussex, which is where I ended up in the UK. He had been a student in Oxford, as I had, and he had met a doctoral student from Ghana at that time. And a few years later, they met up at some international conference or whatever, and the Ghanaian, who by that time was not only back home but was head of department in the physics department at the University of Science and Technology in Kumasi in Ghana. This head of department suggested that we set up an exchange arrangement between Sussex, the University of Sussex, where Douglas Brewer and I were working, and the University of Science and Technology. The arrangement was that they would send across one of their junior faculty members to try to finish off a PhD in a better environment, as it were, and we would send off a faculty member for their heaviest teaching semester, which was the fall semester, each year. Well, the first year, one of my colleagues went and had a good time, and nothing went wrong much. The second year, I volunteered to go. And so I went for the fall semester of, I think, 76. The third year, I wasn't particularly anxious to go again, but none of my colleagues seemed anxious either. So in the end, I felt I should volunteer again, and I did. I was somewhat dismayed at the prospect of having to do a third year, but I was actually, somewhat unfortunate, to be honest. I was somewhat I was saved by that from the fact that one of the phenomena, sort of recurring phenomena in Ghana, at least in those days, we're talking about the mid-70s, one of the recurring phenomena was the coups. So they used to have a coup every 2 years or so. And, I mean, it didn't mean much. Generally speaking, what it meant was that they just renamed a couple of the major streets downtown and so forth in honour of the new regime. But things went up pretty much as they had previously, and no one took all that much notice of it. Unfortunately, and I think 1977, they had a rather more serious coup when people did actually get killed. I mean, in the previous coups, they were pretty bloodless, really. But this time, people really did get killed, and the university got involved, and as a result, the authorities shut down the university for a semester, which totally put their timetable out of kilter. So so in fact, the arrangement was discontinued. So I went for those 2 years in the fall of 76 and 77, in fact. And I found it very interesting in perhaps a rather different kind of way. In this case, I didn't really I made some attempt to learn the basics of the language, but I can't in this case. But I didn't have a lot of opportunity. I mean, there was no systematic teaching, language teaching or anything like that. So my knowledge of Akan is very, very basic indeed. And again, it wasn't too easy to mingle in most of the society, because of course most of the society, as it was, located in the villages around outside the main town where the university campus was. But it's nevertheless very interesting, for example, to see the difference that their childhood experiences of technology or lack of experience made to my students. I actually volunteered in the second year that I was there, to the horror, I should say, initially of my colleagues, to supervise the first year labs. They said, "You can't do that, you're a theorist."
You weren't qualified?
No, I was not qualified, but I took the point of view, which unfortunately turned out to be correct, that the sort of unconscious common sense, I would call it, or most people I think would think of it as physical common sense, which I'd picked up in childhood and adolescence simply by messing around with odd bits of equipment and so forth. I mean, not at all complicated. I mean, it wasn't a matter of taking the radio apart to see out how it worked, something much simpler than that. It nevertheless gave you a sort of physical common sense that many of these kids who came directly from the villages, they just didn't have. I mean, in the villages, if you grew up in a Ghanaian village, the odds are that the most sophisticated product of traditional technology that you would have seen is just a simple hand loom. And by Northeast Asian standards, the Ghanaian hand looms were really very, very straightforward and I wouldn't say primitive, but certainly not at all elaborate or sophisticated. And you go from there directly to the motor car. And so, of course, then the motor car is just a black box really to you, even more so than it was to me. So I did find, so in some sense it was a bit embarrassing really, but I did find that in many cases these people just didn't have the kind of common sense. That wasn't universally true. Some of them were really very much on the job, and they really figured out how quite complicated bits of electrical equipment and so forth worked. But by and large, they didn't really have that background. So.
Did this experience make you a better teacher?
Who knows? You'd have to ask the students. I did. What I can say is that many years later, this maybe only something like 10 years ago, I was at a conference somewhere in the American South and ran into a guy who was teaching there who remarked he was from Ghana, and I said, I spent a semester at UST and whatever, and he said, yeah, he taught me. And he seemed very happy about it. So.
Well, that's good feedback that a former student came to see you and spoke highly of it.
Yeah. So. But I'd have to say that I didn't really like the way the courses were organised, or the kind of syllabus they had, because this is based almost entirely on the British system, since Ghana, of course, had been a British colony in the past. They were just really teaching standard electromagnetism, standard stack mech, etc., etc. Wasn't really, I think, what these guys could use. The thing is, in a country like Ghana, and you have to remember that really, if you look at Africa or sub-Saharan Africa, excluding, say, South Africa and Zimbabwe and so forth, but if you look at most of sub-Saharan Africa, Ghana is relatively ahead of the flock in most things, but nevertheless, they have a huge shortage of just basic everyday mechanical skills there. And so all sorts of things which have to, which in Europe or America, you'd assume you just farm out to some kind of specialist company or whatever. In Ghana, those have to be done by the university, because the university is the only place that can do them, basically. One example of this was that when the UST, the place I was working, they had some kind of anniversary they wanted to celebrate, and in connection with that, they wanted to have a university flag and erect it on a flagpole. Well, I mean, I think probably if something like the University of Waterloo was doing the same thing, they'd routinely just sent off an order to the local engineering firm to build the flagpole, and they sent off an order to the seamstress specialists to sew an appropriate flag and so on and so forth. And this would all just be done as a routine part of everyday business. Well, you can't do that in Ghana. Such places don't exist. It had to be the engineering department of the university which erected the flagpole. It had to be the fine arts department of the university which sewed the flag, and a lot of things go like that. So really, I think what's needed was to train a lot more people at a level which in Europe or America would not usually be regarded as the province of the university, something much more basic, as it were, but nevertheless very essential to the functioning of the country. One of the big problems with I certainly experienced when I was in Ghana was that you had all these aid organisations in Britain and Germany and whatever, which were sending out these nice fleets of shiny buses and so forth, which were intended to revolutionise the transport network of a particular region. Well, they got there, and after a few weeks or a few months, they broke down, and no one was around to fix them, basically. And so the whole aid program really rather ran into the ground.
There's sort of a presumption that what works in the places that we're from will work somewhere else, but that's not the case.
It doesn't. And, I think I was not the only one of the among the expatriate teachers in Ghana, of whom there were quite a few, and many of them had been there a lot longer than I had. But I think most of them would agree with this.
So I'm sure a lot of our listeners are just waiting patiently for us to ask you a bit about the Nobel Prize. And you've shown us already that you're such a great storyteller. So would you mind telling us the story of how you found out you won a Nobel Prize?
Yeah, well, it's a fairly easy one. It had occurred to me vaguely. I mean, I would be dishonest, I think, to say it hadn't, that I might possibly get the Nobel Prize someday. But I mean, this does sound a bit arrogant, but I'd actually, when insofar as I thought about it at all, I thought it was more probable that I'd get the prize for the work I'd done on quantum foundations, because I thought that in the case of helium-3, superfluid helium-3, they'd already given a prize to the 3 experimentalists, and I thought that was probably the lot that they were going to give for that. Anyway, so I hadn't particularly worried about it. In particular, I don't think I'd made a note of October, whatever it is, on my calendar. A lot of people I hear do, but I hadn't.
I was up at 5:30 in the morning watching the recent Nobel announcents. So I'm one of those people.
Okay, well, congratulations. You're much better.
And I'm not even in the running for one.
But you have to write about it.
Yes, I do have to write about it.
Anyway, so here was I sleeping soundly in my bed at something like 4:30 in the morning, and then the phone starts to ring, and my first thought is that this is one of my in-laws in Japan who's got the time difference the wrong way round, which they're always doing, and calling in the middle of the night at some totally inappropriate hour. So I stumble out of bed blurry-eyed and go to the phone. And I pick up the phone, and there's a voice on the other end which says, am I speaking to Professor Anthony James Leggett, rather formally? And I say, well, yes, that's me. He said, well, this is so-and-so of the Swedish Academy of Sciences in Stockholm, or whatever. And he says the physics committee of the Swedish Academy of Sciences, this organisation has debated concerning the Nobel Prize for 2003. And they have decided to award the prize to Professor Vitaly Ginzburg of the Lebedev Academy of Sciences in Moscow, and various qualifications, and to Professor Alexey Alexeyevich Abrikosov. I was thinking by that time, what's this got to do with me?
Why are you telling me this at 4:30 in the morning?
And finally, Anthony James, Professor Anthony James Leggett of the University of Illinois at Urbana-Champaign. So I think my first thought, as I suspect is a lot of people, is this has to be a hoax. But I decided I wouldn't just put the phone down. At least I'd go on listening, and so he went on about various things. But the thing which I think really convinced me that it was probably for real was that he said, "Look, I have to warn you one thing. You over the next we're going to announce this prize at such and such a time. I think it was 12 o'clock in Stockholm, so 5 o'clock a.m. in a few minutes in Central Daylight Time."
You only found out a few minutes before.
Yeah. And so once this happens, you're going to get a lot of calls from journalists and so forth, and so you should make some as best you can, some kind of arrangement to handle these calls. And I thought that's not something a hoaxer would think of somehow. So I finally got convinced that was right.
And I think your case is kind of particularly unique because, as you said, you shared this prize with two other researchers, Alexei Abrikosov and Vitaly Ginzburg. And of course, I know that you've referred to them as giants in the field, and many people would have, but their contributions were many years before yours. So how did you react to finding out that you were sharing the prize with these other researchers?
Well, to be honest, I was slightly puzzled, and but I mean, look, I know, although obviously this is not the sort of thing that's public knowledge, but I'm pretty sure that the experimentalists, in particular, the Cornell experimentalists, lobbied hard for me. They and I'm sure they're very effective in doing so. But yeah, I mean, my feeling, frankly, if I think about it seriously, then logically, if they were going to give a prize mostly for pre-BCS superconductivity, I mean, there's no reason they shouldn't. But if they were going to do that, I really think there was another person besides Ginzburg and Abrikosov who had a very good claim for that, and that was Pippard, Brian Pippard. Well, but I'm not complaining they chose me, but in some sense I think it was a bit out of the, as you say, a bit out of the ordinary logical structure of the prize. Yeah. This is a question, of course, I used to get at press conferences and so forth. People would ask me, did you collaborate with with Ginzburg and Abrikosov? And I'd have to say, well, you know, when Ginzburg and Landau actually were doing the work, which eventually qualified them for the prize, I was 12 years old and living on the wrong side of the Iron Curtain. So no.
And how does winning a Nobel change your life?
Well, one thing that's certainly changed is that I tend far more than I did previously to get asked for my opinion on matters often of concerning world politics or sociology or whatever, on which I really don't feel I have sufficient information to give a sensible answer. So I usually try to dodge those questions as best I can, but in some cases I feel that the cause is sufficiently worthwhile that I do try to find out enough, having been asked the question, or asked to sign a petition usually, or whatever. I try to find out enough about the issue in question and the pros and cons, and to decide whether I can honestly sign the petition or not.
You're giving a talk here tomorrow, and I've noticed the title of the talk is The Serendipitous Road to a Nobel Prize.
Yes, right.
Can you speak to the idea of serendipity and what role that plays?
Yeah, well, the most serendipitous event, I think, in my whole career really was the elevation of Sputnik in the fall of 1957, because that was what basically enabled me to switch from my original course of study in Oxford, which was on the humanities side, the Oxford Greats degree, to switch from that to physics. Had it not been for that, I think the whole idea of someone who had no experience, well, it's not quite literally true that I had zero experience of physics at high school, but to all intents and purposes I had no experience of it. Someone who had no meaningful experience of physics at high school, and had not taken any undergraduate course in physics, whatever, suddenly to start a second undergraduate degree after finishing the first one in humanities, I mean, they've just been knocked out of court, I think. Luckily, the Sputnik changed popular attitudes quite a lot, and one of the things it did was to make a lot of people question the idea, which in some sense had been a sort of given in British society up to that point, that the natural thing for people who were intellectually talented in any way was to study things like the classics or perhaps politics, philosophy and economics, PE, the Oxford degree, and then to go into some kind of governmental role in the civil service or whatever. Not a great deal of attention had been paid to the education of scientists, and in particular to making sure that people who really had an aptitude and certainly a zeal for science could actually go into it. I mean, I never really had that opportunity, rather surprisingly actually, because my father was in fact a school teacher of mathematics, physics and chemistry, but he never really put any kind of pressure on me to study in that area. In fact, rather the opposite. He encouraged me to go into the classics. So, again, I think he was a sort of victim of his time in that respect.
Yeah. So the launch of Sputnik just put in the public consciousness this idea that studying science could have a real important practical outcome? Is that?
Well, yeah, I mean, basically, I mean, the cry went up, how come that the Soviets have got ahead of us in this incredibly important technological field? And of course the answer was, well, we've encouraged all our best people to go into useless things like classics and not into useful things like physics. Mm-hmm. So I was not by any means the only person who tried to make the switch at that time. In particular, I remember maybe half a dozen people in my year at Oxford had done a first degree in history and then decided to switch into chemistry, and I don't think that ever really worked out for any of those people. And I mean, I think I can sort of see why, because really chemistry and physics are somewhat different in the fact that this far, I suspect at least, I mean, I've never really had any proper course in chemistry, so I can't really tell, but I suspect that much more of undergraduate education in chemistry consists of just learning facts and reactions and so on and so forth, whereas physics is a great deal more organised, as it were, gives you a much clearer intellectual pattern.
Mm-hmm. Is that organisation part of what drew you to physics? Is this organisation that you just mentioned, is that part of what drew you to physics?
Okay, what drew me to physics specifically? That was a sort of indirect process of argumentation with myself. I think my the first step along the road was sort of negative, really, in the sense that I was very immature. I mean, in retrospect, when I came towards the end, I first started thinking about my future career at, let's say, sometime around the end of the third year of my four-year degree in Oxford. Suddenly realised that I was going to have to do something in life for which someone else was going to pay me. I couldn't go on being a student forever. So at that point, I really had no experience outside of high school or university undergraduate work. I mean, there was no Peace Corps or anything equivalent in those days. I tried rather a desultory way to find a short-term job for the last 2 semesters of what would have been my high school career. Didn't work out, so I had to stay at school. Then 3 years of undergraduate study. So no experience really of life outside some kind of academia. So I was just pretty unimaginative, frankly. I just thought, what am I going to do in life? Well, I look around, I see what are my classmates or the earlier years. What have they done? People who've graduated in this particular course, grades course. Well, the answer was mostly either they had gone into the British civil service or they had become teachers of one of the subjects they studied. These were classical languages and literature, ancient history, ancient Greek and Roman, philosophy. And I took one look at the civil service and I thought, really, this is not my cup of tea at all. I'm not going to be good at it. I'd probably even failed the civil service exam, I imagine, had I taken it, because I just don't have the right kind of skills. So that was not an option, really, for me. Well, so it had to be teaching, basically. So which of the three subjects? Well, I'd enjoyed all three, but the one I really, I think, enjoyed most of all, probably done best at, was philosophy. So it had to be philosophy. So I started thinking a little more concretely about this. So what I'm going to do. I'm going to get my final degree in grades. I will apply for a postgraduate degree in philosophy. Eventually I'll get that after 3 years or so. I will then, in those days probably I would have gone straight on to a junior faculty position. I would end up in incidentally, school teaching was not an option because philosophy just isn't taught at high school level in the UK. At least it wasn't in those days. So it had to be university. So I will end up as a faculty member in the Department of Philosophy at a university. End of story. That's my career. The more I thought about this, the more I realised I somehow just didn't want to do this. And so I started thinking, what is it exactly that I don't like about this prospect? And well, I mean, I think had I had a little more experience of life, I would have thought maybe I'm should not really be thinking about going into academia at all. Maybe I should go and become a rock climbing instructor or something, where it would have been terrible, incidentally. But that didn't occur to me, so it had to be something about philosophy, specifically as a subject. I started asking myself, what exactly is it? Why is it that I don't want to spend my whole life doing not just teaching, but presumably also research in academic philosophy? And the more I thought about it, the more it seemed that it was because, at least as it was practiced in Oxford in those days, what counted as good or bad work in philosophy seemed to be so much a matter, first of all, of how exactly you phrased your conclusions, the exact nuances and turns of phrase, and secondly, of your colleagues' opinions of what you've done. There really didn't seem to be any kind of hard touchstone of whether what you were doing was good or bad work, whether it's correct or not. And so I started thinking, I really want to go into some area of academia where there will be this an external touchstone of whether what I'm doing is good work or not. And I had by a series of coincidences, I'd had a very little exposure at high school level to modern mathematics. And so my first thought was, well, perhaps I should become a mathematician or try to become a professional mathematician. And then I remember very clearly saying to myself, no, I don't want to become a professional mathematician. Why not? Well, because in mathematics, by the very nature of the subject, if you're wrong, it means you're stupid. I would like to be able to be wrong without being stupid. And so I started, in some sense, at least subconsciously, looking for a subject where I could be wrong. That is, I could make sort of conjectures about the world which were not trivial, but which nevertheless might be right or wrong. And then either I or my colleagues could go out and find out whether they were right or wrong. And that's how eventually I came to physics. I think, frankly, were able to make the choice again, I could easily have plugged for engineering rather than physics. But that was a period, and I was at a stage of my career where it seemed that to be an engineer you had to be good with your hands, and I was terrible with my hands. I mean, I didn't realise there were aspects of engineering where it didn't really apply, but anyway, I didn't really consider that seriously. So physics it had to be, and then of course then all the fun started. I had to actually start making this a reality, and that was highly non-trivial. There were lots of aspects to that. I had to get a university to accept me. Luckily, actually more than one Oxford college did accept me, and I ended up at a different one where they would not only accept me but give me some financial support But the major obstacle was the military draft, because it had already been. We're talking about my graduation in the summer of 1959. A couple of years before that, the British government had decided that the draft would end. And the last intake would be the summer of 59. Now, I'd already got 4 years deferment from the draft to do my first undergraduate degree. I go to my draft board and say to them, look, you guys, I know you've been very generous and given me 4 years to do a degree in grades. Well, I would actually rather like to do a second undergraduate degree in physics. So would you like to give me another 2 years for that? And they, of course, would look at me and say, well, we've got your number. You're just trying to get out of it altogether, which, of course, is what happened eventually. Mm-hmm. But anyway, that did not seem likely to fly. And that, of course, is where Sputnik came in. Because finally, my tutors, again, I'm sure my tutors argued very, very, very hard and eloquently in my favour, but they were able to convince the draft board that I'd be more used to the country doing a second degree in science rather than on the parade ground.
There's actually another question from a student that touches on this idea from a student named Felicity. So let's play that one for you.
So let's listen to her.
Hi, Sir Anthony. I'm Felicity in grade 8. Can you imagine yourself in any other profession?
Well, I did in the past. When I was 5 years old, my ambition, believe it or not, was to become a railway signalman. I was very fascinated by the way the signals worked, etc. A bit later than that, my ambition was to become an explorer. In those days, there was no GPS or anything like that, so there were still fairly large tracts of the planet which had at least not, I mean, they may have been inhabited or not, but they were certainly not systematically mapped or whatever, so that was not totally unrealistic. But nowadays, yes, I think I could. And had I got to start my career again, then I think I'd probably plump for something like experimental neuropsychology. And the reason for that is partly that I think it's full of very fascinating questions, but secondly, that, well, it really is much more direct practical use to humanity than doing research in the foundations of quantum mechanics or in superfluid helium-3 or whatever. Mm-hmm. So I think I probably would go in that direction. Whether I'd be successful or happy or not in that career, I don't know, but I think that's what I would do.
There's actually a related question. I put up on an internet forum, I said, I'm going to speak to Sir Anthony Leggett. Would you have any questions for him? And we received a question from someone named Douglas that is related to this topic as well.
Hi, Anthony. My name is Douglas, and I'm a student of physics in the University of Maryland. And as someone who's about to go to a physics PhD, I'm very curious to hear from you what do you think are the most promising and exciting fields of physics right now? And if you were to choose your field and your career path right now, would you choose, say, low temperature physics again and condensed matter theory, or would you go for something else?
Okay, thank you, Douglas. That's a good question. I don't know if you're familiar. I'm addressing Douglas now. I don't know if you're familiar with the late Thomas Kuhn's distinction between so-called revolutionary and normal science. The idea is that for most of the history of science, things are done according to what he calls a particular paradigm, which basically sets the kind of questions you can ask, the kind of answers you're allowed to give, etc., etc. And then, very occasionally, there are these revolutionary periods when all the rules change, and in some sense, the subject comes out of that revolutionary period looking quite different from what it was when it went in. And he cites, for example, the Copernican revolution in the history of physics, the quantum mechanical revolution, special relativity, etc., etc. Mm-hmm. Addressing again Douglas, I think you should ask yourself, would I rather work in a normal or a revolutionary period of science? At first sight, you might think it's much more exciting to work in a revolutionary period. On the other hand, if you want to, as it were, get a certain minimum achievement in your career, that may not be the answer. It may be better to work in a normal period when, you have well-defined rules according to which you can operate. If you work hard and are conscientious and so forth, the odds are high that you will make a successful career, publish the appropriate number of papers, etc., etc. So that's one choice you have to make. But then, of course, suppose you do come out with the revolutionary answer, then in which area of physics is a revolution most likely to occur? I think I would have to say that probably not very likely in most current areas. The only one in which I do see a possibility is cosmology. I'm a total outsider in this. I'm speaking from ignorance, but my impression, at least for what it's worth, is that many of the ideas which are floating around in cosmology, dark matter, dark energy, these are to some extent really band-aids, and that there's something much deeper that may be wrong and may eventually be overthrown. So if I had to bet on where the next major revolution in physics is going to come, it would be in that area. Other than that, would I go for low temperature physics? I might, I think, because low temperature physics is one area in which you see how the interaction of many particles, which individually may be rather boring, how the interaction and collaboration of those particles may produce effects which are qualitatively quite unexpected and novel. You'll notice I've not used in that sentence the word emergence. I hate it. I hate the word emergence.
Oh no, I was about to use it. Why do you hate it?
Why do I hate the word emergence? Well, I'm sorry, I shouldn't say I hate it, period. That would be too strong. I mean, I think there are valid uses of the word emergence. For example, if someone says that space and time are emergent from a deeper level of reality, which is based on quite different kinds of concepts, I think that's probably a valid use of the term. What I hate is when people talk about, emergent superconductivity, as is actually the title of an institution I worked in a few years ago. I hated it and the reason I hate it there is that essentially there is no topic certainly no interesting topic in the whole of condensed matter physics which is not, quote, emergent, unquote. So saying that something is emergent in that context, there's nothing to it. It's just a buzzword, nothing more. But anyway, getting back to the low temperature physics. Yeah, so that's what I like about low temperature physics. And moreover, unlike say high energy physics, it is a tabletop kind of area. You can not only make conjectures, you can actually do experiments, or at least get your colleagues to do experiments, often within a time scale of a year or two on these ideas. For example, I did this on one occasion. I had an idea concerning superconductivity, and sure enough, within a few months, my colleague Delvin Harlingan and his collaborators had actually done it, an experiment. So that's what I like about low temperatures, but I think I might again be somewhat drawn by the fact that there are areas of physics which are both intellectually exciting and have much more direct human relevance. And one of those would obviously be neurophysics, or more generally biophysics, but neurophysics in particular. So I think I might well make that choice had I got to do it again from scratch.
You've already given some specific advice to someone who's deciding to pursue a PhD in physics, but do you have other advice for students that might be earlier in deciding that they like science, but they're maybe still deciding what they want to do from there?
Okay, do you mean, say, whether to choose physics rather than some other science? Or
Maybe I'll rephrase. Do you have more general advice for young students who are interested in science?
I think my first piece of advice would be do follow your own curiosity. If there's a question which you feel you don't understand and you have a suspicion that no other people aren't understanding it too well either, well, really beaver away at it, follow it up. Don't worry if other people shrug their shoulders and say, that's a silly question, everyone knows how that works. Remember, I always say remember Einstein. For 250 years, people have been sort of taking it for granted, or most people at least have been taking it for granted, that if an object is dropped in vacuum, whether it's a feather, a stone, a pencil, or whatever, it will fall with exactly the same acceleration. They're sort of taking it for granted ever since Galileo, basically. Einstein asked why. Why does this happen? Now, I'm sure that when he asked that question, a whole lot of his colleagues say, that's a stupid question, they just do. Everyone knows that. Mm-hmm. Well, so don't take that as an answer. Just follow away at it and wait, work away at it until you find an answer which at least is satisfying to you, whether or not other people agree with it or not. And in the process of doing that, the second point I would say, don't worry too much about the existing literature. I mean, well, if you're at undergraduate stage, perhaps you're not reading Physical Review or Phys Rev Letters, I don't know, but you will certainly at a graduate level. I would say don't go away and find every single paper that's been written on the question you're interested in the last 50 years. That's usually a disaster because these papers will all give contradictory ideas and so on and so forth. No clear picture will come out of it. Just do it, try as much as you can, try and do it yourself from scratch, from really rather basic principles. That I was very lucky to be able to do that, pretty much by accident, not more than by design. But when the experiments on superfluid helium-3 came up in 1972, these were on nuclear magnetic resonance. There are lots of textbooks on nuclear magnetic resonance, including a very nice one by my colleague Charlie Slichter, my late colleague at Illinois, and so forth. I hadn't read those textbooks, and I made a quite conscious decision not to read them. It's because it seemed to me that what was going on in this experiment was so anomalous and so out of the ordinary that it couldn't be any of the things which were handled in these texts. So I decided just to try to do it from first principles, and was lucky eventually that worked out. Of course, once you've got your solution, then of course you don't want to rush off and publish it without checking that it hasn't been known for 100 years, and sometimes you'll find it has, but it doesn't matter. It doesn't matter it's been known for 100 years. You did it yourself. Almost certainly you'll have learned something that you would not have learned had you just read the existing literature. Point 3 is don't feel that any honestly conducted piece of research is going to be wasted. You may feel that you've had this research project and it's just sort of run into the ground. You know, the experiment just didn't work, or the theory didn't give the result which you thought it ought to give, or whatever. But anyway, you had to basically abandon it. Well, don't just leave it there. Write it up. Write it up carefully. Put it away in a drawer. I would bet that 10, 15 years down the road it will come back and help you out in some perhaps apparently totally different problem. That happened to me when I worked on two-band superconductors during my postdoc year in Japan. It turned out that I was working, and what had triggered my interest in this subject was a particular experiment which seemed to show that particular metal, niobium, was a two-band superconductor. So I went away and did the theory concerning that. A few months later, second experiment came along and showed it wasn't really a two-band superconductor after all. So at first sight, my work was totally wasted. But no, I did write it up. I put it away and remembered it. And 8 years later, when the helium-3 problem came up, that was in some sense the key to solving that. So, fourth piece of advice: make things simple. if you possibly can, don't look for the most elegant or the most sophisticated way of describing a phenomenon. This is really for the theorists, people who are going to be theorists, I guess, but try to find some simple idea which is equivalent, even though it may not look as elegant as the more sophisticated formalisms. Again, helped in my own work, or my first non-trivial work on superfluid helium-3 before it was experimentally discovered. I started off doing it with very highly sophisticated Green's function field theoretic formalism. And I got a particular result which I didn't understand. And I could have just rushed off and published that result, but I thought, no, I don't, not understanding it. I have to find something simpler. And so I worked at it a bit, and eventually I did find a way of putting it which was much, much more straightforward and simple. In the meanwhile, my Russian colleagues were typically working away with these high-powered Green's functional formalisms, and they basically discovered the same result, but they didn't realise they discovered it. Anyway, so that's that. And finally, I think in some ways the most important piece of advice, assuming that you're thinking of going into academia or possibly into high school teaching rather than, say, industry, and if that's the case, then whatever else you do, then take your teaching at least as seriously as you take your research. That's going to be not just good for your students, it's going to be good for your research also. I find that many of my most fruitful ideas have, at least indirectly, come out of courses I've taught both at the undergraduate and postgraduate levels. So remember, whatever else you remember, you are not just a researcher, you are a teacher.
Well, Tony, thank you so much for sitting down with us today. This has been an absolutely fascinating conversation, and I'm so thankful that you joined us today.
Well, it's been a pleasure for me too.